a section of our work is going to involve using integration by substitution. So when we use integration by parts, sometimes you have to use integration by substitution inside of integration by parts. Integration by parts is a very, very powerful technique of integration. So is integration of partial fractions. And as I said, we are spending the next 5 days of classes on this material. 2 on parts and 3 on partial fractions. So what's the goal today? To be able to integrate using the method of parts. There's a formula here. And I mean, I guess I'll give you the formula for exams. But you will have used it so often that you will know exactly what it is you need to do. And I think it's important that you understand where the formula comes from. So consider not integration, but consider a product of functions that you're going to differentiate. So I'm choosing f of x times g of x as being 2 functions that are multiplied together. And I'm saying let's differentiate that. You will see why as the lesson proceeds. Well, I would use the product rule. And I'm choosing to write it the way the textbook writes it. Normally what I would say is derivative of the first times the second plus first times derivative of the second. Here I'm just saying second times derivative of the first plus first times derivative of the second. That shouldn't bother you. Okay? And now what we need to consider is this, that the antiderivative of a derivative gives you the original thing. So if I say what is the antiderivative of the derivative of p of x, it's p of x. And what I'm about to do then is just take the antiderivative of both sides. Well, how do we write the antiderivative? We write this. This notation means you are anti-differentiating what is inside. And I don't mean to confuse you here, but it just makes the most sense to me in terms of where I'm going with this. I've switched sides here. What's on the right-hand side, I'm writing on the left. And what's on the left-hand side, I'm writing on the right. So when I anti-differentiate this, I get the original thing that I differentiated. In other words, the antiderivative of this will give me the f of x, g of x. We learned something a couple days ago with the fundamental theorem of calculus, and that's that this thing that's on the left-hand side is an integral of a sum of 2 things. And an integral of a sum is the sum of the integrals. It doesn't work that way with derivatives, or it does work that way with derivatives, but it doesn't work that way with all things. So now I've got the integral of g of x f prime of x dx plus the integral of f of x g prime of x dx equals f of x times g of x. And I know as a student you go, what's going on here? Why are we doing this? You will find out again as the lesson proceeds. I'm going to choose to rearrange that for the integral of f of x g prime of x. And I get that. And this is the integration by parts formula. It's a formula that will allow you to integrate things that you otherwise couldn't. And what we've done here, well, what I've shown you that somebody has done here is take something that is an integral, the integral of f of x g prime of x, and write it in a different way. And this is the basic idea, that your questions are going to be, what is this equal to? And you're going to look at it and go, I have no idea how to do it. In fact, I cannot integrate that. But if you apply the integration by parts formula, you will get, instead of that, you will get this, which contains another integral, a different integral, which you'll look at and go, that's easy. This is the whole purpose here, is to write an integral that is difficult, the one on the left, and write it in terms of a different integral that's simpler to integrate. So this is something you can't do. You don't know how to do it. But you say to yourself, and we'll learn why we decide to do this, you say to yourself, you know what, this is a candidate for integration by parts. You'll apply the integration by parts formula and discover that you get an integral that you can do just by looking at it. So, I mean, I really shouldn't say the one on the left, you can't do it. You can't do it until you change it into the stuff on the right. For example, if I asked you what is the integral of 3x cos 4x dx, before today, I could give this to you and you would fumble around in the dark, figuratively speaking, and very few people would be able to figure it out. It would be a total trial and error thing. You'd try something, you'd think, well, maybe it's going to be this, and then you try differentiating your answer and you go, no, that didn't work. But if you apply the integration by parts formula and you don't know how to yet, you will get this. And this integral over here you can do. I'm not sure how many of you see, we'll talk about this a little bit later in detail, that this will be negative 3/16 cos of 4x. Because if you differentiate that, you get negative 3/16 sine of 4x times the negative, because the derivative of cosine is negative sine, and then you have to multiply by 4. If you don't see how to get that, then how you would determine this is you would use substitution here. You'd use what we learned yesterday. But the point is, this you can do. Okay? Is there a question? No? Okay. So it's used to take a difficult integral and express it in terms of a different integral that's simpler to integrate. One part, and the part here is a factor, one part of the integrand is chosen to be f of x. That's the original integrand. One part is chosen to be f of x, and one is chosen to be g prime of x. This f of x that you choose has to be something you can differentiate. Because you're going to pick a piece, it's actually called a part or a factor, of the original integrand, and in the formula it turns into f prime of x someplace. So whatever you choose, you have to be able to differentiate it, because you have to write the new integral, which contains f prime of x. Whatever you choose for g of x, or g prime of x rather, you have to be able to anti-differentiate it, because whatever it was is going to become g of x on the other side of the formula. So you're going to choose something for f of x which you will differentiate, and something for g prime of x which you will anti-differentiate. Generally speaking, and this is not always the case, there's going to be an exception. Generally speaking, whatever you choose for f of x is going to be the thing that gets simpler. So in these two examples here, I have the integral of x sine x dx. If we chose f of x as being x, if I did this, then that x over here is simply going to become 1, right? And 1 isn't even something we have to worry about. It doesn't even have a variable. On the other hand, if I choose in the second integral, if I choose this as f of x, then I go f prime of x to proceed to the right-hand side, then f prime of x is 3. It becomes simpler. Okay. In the first integral, the x part would become simpler if differentiated, and in the second, the 3x plus 4 part would become simpler. So that's the piece you're generally speaking going to choose to be f of x. Boy, this thing is touchy today. There are obviously exceptions to most rules in mathematics, and we are going to look at, I think even today we'll see at least one example where you do not want to choose the thing that becomes simpler as f of x. because then you paint yourself into a corner. So enough talk. Let's see how this works. Let's integrate x sine x dx. What is the antiderivative of x sine x dx? One thing I didn't mention is your integrand has to be completely covered with f of x and g prime of x. With substitution, we could deal with constants and coefficients and not worry about them. So this entire integral is going to be broken down into two parts for the integrand. F of x, which we're going to write here, and g of prime of x, which we're going to write here. Right? That's what we're doing. This is the setup. But in order for us to write out what this is equal to, look at what this is equal to. It's equal to f of x times g of x. Well, then we're going to need to know g of x, aren't we? Minus the integral of g of x f prime of x, you're going to have to know f prime of x. And I'm trying to just give you a playing field to learn from. Once you choose f of x and g prime of x, you differentiate f of x and you anti-differentiate g prime of x. So clearly, whatever you choose for g prime of x, you better be able to anti-differentiate it. But what have I suggested to you? I've suggested that you choose for f of x the thing that becomes simpler. And that means that for g prime of x, we have to choose sine of x. So this is just what we've chosen. Now we have to proceed. We differentiate x and get 1. We anti-differentiate sine x and get negative cosine of x. And if you think you're never going to make a mistake with the negatives on the cosines and the sines, think again. Okay, I have to double check this now. Is the derivative of negative cos going to give you sine? Yes. So what is this integral equal to? It is equal to, and what I'm going to draw on this box is a visual that might be helpful. It will always be equal to the product of these two. Right? If you look up here, it's equal to f of x, g of x. So we have to multiply those two. And then the formula says minus the integral of g of x f prime of x. So it is always then going to be minus, this is always going to be minus the integral of the product of those two. So we are going to have minus the integral of 1 times negative cos of x dx. Let's simplify this. Let's just write it a little bit easier on the eyes. We have negative x cos x. Why don't we just go plus the integral of cos x dx? Because there is, after all, just a coefficient of negative 1 there, and we've learned over the past couple days you want to start taking those coefficients out if you can. And I don't know why you would want to subtract an integral of a negative integrand rather than just add the integral of the positive integrand. Does that make sense? Okay. Well, this, you can do this in your sleep. Well, if you're dreaming about calculus, it's a very easy thing to do in your sleep. The antiderivative is sine of x. And that means that the integral of x sine x dx is equal to negative x cos x plus sine x plus your constant. And I don't believe, if I gave you 10 minutes, I don't believe too many people would be able to say to themselves that this is what you differentiate to get x sine x. I don't think it would have occurred to you to go down that path. It might now to explore that. Just to convince you of this, if that is right, then the derivative with respect to x of negative x cos x plus sine x better give us x sine x. That's, after all, the test for how we determine whether antiderivatives or integrals are correct. When I differentiate with respect to x a sum, I can differentiate with respect to x the sum in pieces. The derivative of a sum is the sum of the derivatives. So let's see what happens here. I need to use the product rule here. So the derivative of negative x is negative 1 times cos of x plus the first, which is negative x, times the derivative of the second, which is negative sine of x. I think you see where this is going. Plus the derivative of sine, which is cos of x. Beautiful thing happens. We have negative cos of x and cos of x, which is a wash. And then the middle term that I've written there is x sine x. Any questions with the work we did here? All right, let's try another one. And we're not doing too many examples today, just I think 3, and then we'll get lots of practice. The integral of e to the negative 2x multiplied by 3x plus 4 dx. So what would we choose here, Christian, as f of x?
3x plus 4.
Right, 3x plus 4. Because, and I'm going to actually cut to the chase here. It's going to be, this is going to be the product of these two, right? But more importantly, it's minus the integral of the product of these. So if we choose 3x plus 4 as f of x, that new integral doesn't contain 3x plus 4. It contains something simpler. It contains the number 3. And a simpler integrand makes our integration easier. That would mean we would have to choose e to the negative 2x as g prime of x. So now, substitution, which we learned yesterday, is an amazing, useful tool. However, I think even though you can use substitution to determine the antiderivative of e to the negative 2x, I think this is one of those ones that's in the realm of us just looking at and going, it must be negative 1/2 e to the negative 2x. Okay? If you can't see that, then this is what you have to do. You have to go, okay, I'm going to go to a different sheet of paper, and I'm going to integrate e to the negative 2x dx. I'm going to choose u as negative 2x, which means du is negative 2 dx, which means dx is negative 1/2 du. So when I do my substitution, the e to the negative 2x becomes e to the u. The dx becomes negative 1/2 du. You move that negative 1/2 out in front. And you say, well, the antiderivative of e to the u du is e to the u. Which means it's negative 1/2 e to the u, which is negative 1/2 e to the negative 2x, because after all, that's what u is. I guess what I'm saying is, and I'll freeze this up on the screen on the right, is if you need to do that to get that g of x, that's fine. Okay, if you need to, you need to. But that's such a simple antiderivative that I hope you don't have to. If you need to, that's what you can do. All right. Now let's rewrite this. It is the integral of f of x g prime of x equals f of x g of x, so the product of these two, whoops, didn't leave myself enough room, 3x plus 4 times negative 1/2 e to the negative 2x minus the integral of the product of these two, which would be negative 3/2 e to the negative 2x. I'm going to rewrite this. The first term, I'm just going to write it as negative 1/2 e to the negative 2x times 3x plus 4. For some reason, I just think it looks cleaner that way. You're not going to multiply that negative 1/2 into the 3x plus 4 or anything. You just leave it. And then this becomes plus 3/2 times the integral of e to the negative 2x dx. So again, I'm playing around with that rule that we learned the day before yesterday. It's a law of definite and indefinite integrals, that the integral of a constant times a function is the same as the constant times the integral of the function. So that constant in the integrand, that constant of negative 3/2 can be moved out in front, and if I multiply that by the constant in front, which is just negative 1, I get 3/2. And now, this is the point, you can integrate e to the negative 2x. In fact, you better be able to, because you had to do that to get here, right? Because that's what you chose for g prime of x. Our answer then is the following. The integral of e to the negative 2x dx is negative 1/2 e to the negative 2x. So our final answer is going to be this when I multiply the 3/2 and the negative 1/2 together. Negative 1/2 e to the negative 2x times 3x plus 4 minus 3/4 e to the negative 2x plus a constant. For some reason that I don't know, I think maybe because it's just unimportant, we don't worry about factoring these things. There's no usefulness to it. So that's the answer. Any questions with that one? Well, I want to move us away from this f of x, g prime of x nonsense. It's not nonsense. There's a cleaner approach. And it's, instead of saying the integral of f of x, g prime of x, we say the integral of u dv. So our u in this notation is f of x. It's the thing we choose and then differentiate. Whereas dv in this notation is g prime of x. And you'll see in a minute here why it's very useful to use this notation. But dv is simply the thing that you're choosing in the original integrand that you anti-differentiate to get v. Right, so you're going to differentiate u. Why are you going to do that? Because over here on the right, there's a du you need. You're going to integrate or anti-differentiate dv. Why? Because on the right-hand side, you need to know what v is. So, for example, and I just think it's so much quicker and cleaner. If I go back to example 1, then I put x here, and I don't put sine x here. I put sine x dx. And this way, everything is represented. That dx, nobody asked before, but that dx when we were doing it with the function notation was always just something that we had to write. Here, there's a reason for it. What is the derivative of x? Dx. What is the antiderivative of sine x dx? Negative cos x. Look at what happens now when we use this thing that I showed you, that minus the integral of that. Everything is accounted for. Everything. I get negative x cos x minus the integral of the product of these two, and I get negative cos x dx. The dx is part of the product. I don't have to go, oh, right, I got to write that dx there. If we were to take a look at example 2 using the same technique, or the same notation, I guess, this is not just 3, it's 3 dx. This is not just e to the negative 2x, it's e to the negative 2x dx. This becomes negative 1/2 e to the negative 2x. So it's the product of these minus the integral of the product of those but that dx is taken care of. There's a dx there. I was just so tempted to move those constants out as I wrote it, but you can move them out whenever you like. So let's try one more together, and this is the one that proves the exception to the rule that says we want to take the thing that gets simpler when we differentiate. Because you would probably think that you're going to choose x cubed here. Now, does yours say x cubed ln x? Okay. Just imagine, so you're not, just stop writing for a second. Just imagine it didn't say x cubed ln x. Just imagine it said x ln x, okay? And you go, well, Mr. Way said, I want to choose for u the thing that gets simpler, and you do this. Pretty simple, right? Yeah? I know what the antiderivative of ln of x is, but you don't. In fact, to find the antiderivative of ln of x, you need to use parts. You cannot look at ln of x and go, I know what the antiderivative is. I'll tell you what the antiderivative is a little bit later. So even, forget about x cubed, even if it were x ln x, you do not want to choose the part that becomes simpler, because the other part is something you don't know how to antidifferentiate. So now let's get back to reality here. What are we going to choose for u then? Ln of x. dv then would have to be x cubed dx. And antidifferentiating x cubed is not a difficult thing. Again, if you have to use substitution to do it, well, I don't even know how substitution would work there. It's just a matter of increasing the exponent by 1 and dividing by the new exponent. Now, what is the derivative of u? Well, u is ln x. The derivative of ln x is 1 over x. I hope you see why the product of these two as an integrand is going to be something we can deal with, because it's just a product of x's. So the integral of x cubed ln x is equal to 1/4 x ln x minus the integral of 1/4 x to the 4 times 1 over x dx. you know, I would say to you, once you get involved in this technique, you're just following the steps. You're not worrying about what's going to happen or why it's going to happen. What do I get? I get 1/4 x ln x minus 1/4 times the integral of x cubed dx. The x to the 4 over x. Yep.
Why'd you just put 1/4x? Where's the exponent of 4? Because on B, it's 1/4x to the 4.
Can you ask that question again, please, Eli?
In the first part of the equation, when you do UB, you put 1/4x. Shouldn't it be 1/4?
Oh, yes. Thank you very much. 1/4 x to the 4 ln x. The product of these two. I missed that 4 for some reason. So the integral becomes minus 1/4 the integral of x cubed dx, which we can do. So we're going to get 1/4 x to the 4 ln x minus 1/4 times 1/4 x to the 4 which gives us 1/4 x to the 4 ln x minus 1/16 x to the 4. There's certainly patterns here, but they get quite complicated, especially tomorrow. Just as a check here, we didn't check the second example, but we can check this one. This is a product, so to differentiate it, we would use the product rule. The derivative of the first will be x cubed times the second, which is ln x. Well, that's what we want, isn't it? Minus, plus the first, which is 1/4 x to the 4, times the derivative of the second, which is 1 over x. So derivative of the first times the second, plus first times derivative of the second, minus the derivative of this is 1/4 x cubed. Nothing. You have x cubed over 4 minus x cubed over 4, which is gone. Any questions with that example? By the way, how could you conceivably figure out what this is? Well, you would use parts. You would choose u is ln x, and you would choose dv is dx. Which means v is x, antiderivative of 1 is x, du is 1 over x dx. So this integral is the product of these minus the integral of the product of these. X times 1 over x is 1. So what is the integral of x ln x? It's x, sorry, what is the integral of ln x dx? It is x ln x minus x. The antiderivative of 1 is x. You can confirm that the derivative of this product is 1 times ln x plus x times 1 over x. Minus the derivative of x is 1, so you end up with ln x. They get more complicated. Sometimes we're going to need to perform integration using parts twice, and that's what we'll look at tomorrow. Because when we do it once, we get an integral that we still can't crack. But if you apply integration by parts to that integral, you will be able to crack it. So there's a series of questions that you can practice here dealing with integration by parts.